All right, we're ready for our first organic chemistry class that feels really, really organic chemistry, which means we're gonna talk about lots of chemical reactions today. Are we excited about it? Frightened? Okay, let's get started. So here is the general gesture. I'm posting this entire chapter in which we're gonna talk about a lot of chemical reactions with alkenes in this entire chapter. If you look at it, we're constantly facing the question in, like, for example, when the halogen, like HCl, like a hydrohalogen, is added onto a double bond, onto which carbon the hydrogen will add to, onto which carbon the chloride will add to, right? So that's called regioselectivity. We're also facing problem, like, for example, if these two groups are different things, we're forming a new chiral center. The next question becomes, what is the stereochemistry of the reaction, right? So these are the kind of questions we'll constantly discuss for every reaction here. But in order to approach it, I don't want this to become a memorization in which I tell you this is Markov-Naikov, that's anti-Markov-Naikov. It's not very helpful memorizing everything. So my approach of teaching organic chemistry is focused on the reaction mechanism, and hopefully you will be able to derive what is the predicted selectivity for every chemical reactions that we will discuss. All right, so let's get started from here. So this is a quick introduction or quick preview on all the chemical reactions we'll discuss in this chapter. And later on, we'll come back and revisit this table again after our 2 lectures on reaction of alkene and see how much you have learned and how much you know how to predict selectivity for these reactions. So let's get started. First thing first, we're talking about electrophilic addition of an alkene. So this part should be a quick review. Whenever we're talking about a chemical reaction or electrophilic addition, what are we talking about? We're talking about a reaction between a nucleophile and an electrophile. Just in this case, nucleophile, as we know, they are electron-rich species or electron pair donor. For our alkenes, we went over the structure of our alkenes to be your carbon-carbon single bond. And the double bond is a pi electron coming out and above it, right? So remember our burger, both of your bread on top and below the beef patty is our pi electrons. So these pi electrons are nucleophile, or they are a pair of electrons ready to interact with a different species, right? So these are nucleophilic. All right. Now we have nucleophiles. We also have electrophiles. So for electrophiles, what are they? We're talking about electrophiles as low electron density species, or their electron pair acceptors. These electrophiles, they can be neutral or positively charged. If we're thinking about several electrophiles we have already encountered before, or you should be able to identify them as electrophiles. Now, what about the first one? We have an electrophile being my acidic hydrogen. And when we say a hydrogen is acidic, we're saying losing of that proton, we're forming a relatively stable conjugate base. Right, so if my acidic hydrogen is acting as my electrophile, the reaction is called hydration. We'll go over it later on. Now, what about a neutral one? Maybe a hydroalkane, right? So in this case, like HCl, your hydrogen is partially positive your chloride is partially negative. And in this case, my hydrogen will be partially positive. And that's going to be my hydrohalogenation. All right. Likewise, which part of this molecule, this mercury compound, is going to act as our electrophilic site? Anyone want to take a guess? So that's going to be our mercury. Right, so that's going to be my oxymercuration. And what about my BH3? Which part is the most electrophilic or most likely to accept electron pair? So that's my boron. Now, inside my boron, we don't have 4 octet of electron due to my boron is in number 3. So this one is our Lewis acid. And that's our hydroboration. And likewise, if you have a carbocation, your carbocation carbon can also act as an electrophile. All right, so in general, this part are all review, like all on this slide, everything here is a review. Remember our practice of identifying the nucleophilic and electrophilic site. This is identifying the electrophilic site of a molecule that can potentially be used in the electrophilic addition reaction. Yes. So in this case, if you think about how exactly is it going to react, what we're forming is the hydrogen forming a new bond with the nucleophile and breaking this OH bond. So we're forming the stable neutral water. All right, so we're calling this hydrogen being acidic hydrogen. That's in the acid-base chemistry part. And also, we're talking about an electrophilic addition reaction. So remember one of those elementary steps of an electrophilic addition. What is the general mechanism when we're doing the arrow pushing? So that's like if we have a double bond, that's carbon, carbon, and you have 4 different states attached to it, and you have some kind of electrophile. When we're doing the arrow pushing, the arrow goes from your double bond onto the electrophile. We end up forming carbon, carbon. Well, either this one goes onto here, or this goes to here. So that's the general arrow pushing for an electrophilic addition reaction. So these are all the basics. Right, we know where our double bond is. We know what the general arrow pushing is, or direction of the electrons, and we know what are my electrophile. Different kind of electrophile will end up with different name of the reaction, but the mechanism is really the key linking all these reactions together. So we'll start by looking at the hydrohalogenation as a focal point, and then from there, we'll see that most of these alkene addition reactions will have the same kind of pattern. All right, so let's get started with our first reaction. Hydrohalogenation. Now, hydrohalogenation, as its name says, we're adding a HX bond, so a hydrogen and a halogen, onto a double bond. So the overall reaction goes like what we said. We start from the double bond attacking the electrophilic site, which is my proton. And again, this is because your bromine or the halogen is more electron negative, thus your hydrogen will have a partial positive charge. The result here is a carbocation intermediate and a bromine anion. Later on, the bromine anion will attack the carbocation in forming a new chemical bond. Right, so in this part, like you should already know what does this arrow mean, right? So the arrow here means the double bond, electron in your double bond, attacking the electrophilic hydrogen, and we're breaking the HBr bond. The electron in the HBr bond goes onto the electron negative bromine. So we're forming a new CH bond while breaking a H bromine bond. In the second step, the electron of your bromine minus attacks the carbocation intermediate and forming a new carbon-bromine bond. So that's the general arrow pushing. Yes?
Are the Br and H always on the same side or not?
Well, if you think about it, what is my carbocation? Your carbocation is a planar molecule, right? So when the bromine approach that carbocation, it doesn't know which phase it is approaching from. So without a catalyst, this reaction will not be stereospecific. It can attack your carbocation from either the top or the bottom phase. It doesn't know. But we'll come back and revisit stereochemistry later on. And if we draw out what is happening throughout this process on a reaction coordinate profile, this is what we're gonna get. On the y-axis, that's our energy. Our x-axis is our reaction coordinates, right? So what we have on the top, drawing it out. Okay, so what we have on the top, drawing it out, is starting from my reactant. The first transition state will be the partially breaking of the CC double bond and partially forming of the CH single bond and partially breaking of the HBr single bond. And the formation of my carbocation intermediate is here. The carbocation intermediate then undergo a different transition state to form the product. For this process, the more important take-home message is that the first step is my rate-limiting transition state. Or the other way to put it is the first step is the slower step, and hence determines the overall rate of the reaction. Not only determines the overall rate of the reaction, also like selectivity of the reaction is determined by your first step, which is the formation of your carbocation intermediate. Yes?
Is it slower because it's higher energy, or is that?
It's higher in energy, and that's why it's our rate-limiting transition state, or the slower step. And it's higher in energy because we have like higher kinetic barrier there. Yes?
It could be like the other one, though, right?
Well, it depends on the nature of the reaction. Let's put it as the electrophilic addition of a double bond. The formation of the carbocation is always our rate-limiting transition state. All right. And from here, that's the general reaction mechanism. We're pushing the electrons to form a carbocation intermediate being our rate-limiting transition state. There are two questions we want to answer. First question we already addressed, which is what's the stereoselectivity. We'll come back later on. But the other question is what is the regioselectivity? Or AKA, which one of these carbocation is favored? So, next question, regioselectivity. Or where is our new CX bond? So here I want to quickly introduce the Markovnikov's rule, but use it carefully because its application range really limited. So when we say a reaction is Markovnikov selectivity, we're saying in the addition of HX to an alkene, hydrogen will add to the double bond carbon that has greater number of hydrogen. So let's look at an example together. What the Markovnikov rule said is, for example, if we have a cyclopentane with a CH3 substitution, this double bond will react with, let's say, HCl. Let me use a different color so we can tell which hydrogen is which. And we're saying the observed product or the major products is like here we have a hydrogen. If you compare here, we have a hydrogen and a R group. On this carbon, you have 2 R groups. So following the Markovnikov rule, we're saying the hydrogen will be added onto the carbon with a hydrogen already. And the Cl group will be added onto the other carbon. And this product is called the Markovnikov product. Yes?
Wouldn't this create more steric clash though? Like if your hydrogen always groups up with hydrogen and your steric both you really have to.
So here's the key of learning the mechanism. Try not to jump to the question too fast, like before asking steric effects. Let's think about what exactly is taking place in this reaction and see what dominates the reactivity. Remember what we are saying, the rate limiting transition state is the double bond adding onto the electrophile. So what does that mean? So it means the first step, we can always draw our arrow pushing by doing this. Right, where we have the double bond attacking the electrophilic hydrogen, pushing the electrons onto the chloride. And we can potentially form 2 regioisomeric carbocation intermediates depending on where that hydrogen go. So the first one, you can think about, we're forming our intermediate CH3, and the hydrogen goes here and goes onto the methyl group. Or alternatively, you can have the hydrogen go to the top hydrogen, top carbon, and the bottom one with a methyl group got a carbocation intermediate. All right, so from here, remember the first step, we're forming the carbocation intermediate. Now, among these 2 intermediate, which one is the more stable intermediate? So that goes to the stability of our carbocation intermediate. So here's a quick review. We went over the intermediate, the naming of these carbocation intermediates. A carbon with all 3 hydrogen, a carbocation with all 3 hydrogen, that's called a methyl cation, that's less stable than your primary cation with only 1 R group, then your secondary carbocation with 2 R group, and the most stable is the one with 3 R group around it. That's a tertiary carbocation. Right? So in this range, remember your tertiary more stable than secondary, then primary, then methyl carbocation. So back to our question. We now are looking at the formation of 2 different carbocation. This one is, well, 1, 2. This one is a secondary carbocation. And the right one is a tertiary carbocation. All right, so when assigning what's the nature of the carbocation, before you get very familiar with it, draw out the hydrogen on the carbon of interest can be very helpful. So in here, your tertiary carbocation is the more stable carbocation. Now back to the steric question. When we're talking about steric effects, we're talking about the next step, which is your chloride attacking the chloride anion, attacking the carbocation. Now the steric will have a role in my second step when the chlorine approaches the carbocation, will have a little bit of the role. But your second step is not our rate limiting transition state, and hence steric doesn't have a real effect on the overall rate of the reaction, because our first step is our rate limiting step. The formation of the carbocation intermediate is more important, controlling the overall rate and selectivity of the reaction. All right, and well, obviously we say this one is more stable carbocation. And that forms our Markovnikov product. Yes?
I know this is kind of a simple question, but I was wondering like how you figured out that one's secondary, that one's tertiary.
This one? Well, so when we're counting, the question is how do we know which one is tertiary, which one is secondary? Again, this is counting the number of R group around that carbocation carbon, right? So in this case, we look at this carbon with carbocation. That's the only thing we care about. When we're talking about carbocation, we have one hydrogen, one R group, two R group, or some kind of carbon attached to different species. So in this case, we have two things attached to the carbocation carbon, so that's a secondary. On the right-hand side, we have a R group, some kind of carbon, some flavor of carbon, some flavor of carbon around the carbocation carbon, hence this is a tertiary carbocation. All right. So this answers our first question, which is, what is the regioselectivity of this, the hydrohalogenation of an alkene? But things can be more complicated. Well, obviously, the stability of the carbocation or the Markovnikov rule is very useful. But when we have a system, but things can get way more complicated when we're talking about the stability of the carbocation. So moving on. Next question. What's the complication of the hydrohalogenation selectivity? So still, we're focusing on the carbocation intermediate. But now let's look at a different scenario. So, okay, before we go on, just want to refresh your memory on carbocation can be stabilized by resonance. Like if you have an allyl group, and you can have stabilization of the carbocation radical, and that's also going to be more stable. But nevertheless, I want to talk a little bit more about carbocation rearrangement. Let's imagine a reaction like this. We have a double bond, and on here, we have, what's the name of this? 1, 2, 3, 4. So this is 1, 2, 3, 3-methyl-1-butene. Right. So we're talking about the 3-methyl-1-butene reacting with HCl. Again, naturally, following our mechanism, we can draw out the double bond attacking hydrogen goes onto chloride. What we generate is either a primary carbocation or a secondary carbocation. And it's very straightforward to think, okay, so we want to have my hydrogen on the terminal carbon with more hydrogen following the Markovnikov rule, or you don't want to form the primary carbocation. All right, so in here, we're talking about the relative stability of a primary versus a secondary carbocation. So obviously, this primary is not favored. So far, so good. However, it doesn't stop here. If we observe the molecule, we have a potential of forming a tertiary carbocation with a 1,2 shift. So the carbocation rearrangement is another layer of complication, meaning that once we form a carbocation intermediate, you want to pay an additional attention to it to see like whether or not you can form a tertiary carbocation via a 1,2 shift. So this is called 1,2 shift if we count it like 1, 2. So we're shifting the hydrogen on my 1 position into its neighboring position. So this process is going to form a more stable carbocation on the tertiary position, and your hydrogen is being shifted here. Your alkyl group can also be shifted, but the hydride shift is typically faster. Yes? Yes, so in this question, if we're looking at this pair, this is a chemical reaction called 1,2 shift or 1,2 rearrangement. They are not resonance structures because we're actually breaking and forming new chemical bonds. All right. So in here, the result of the carbocation rearrangement is that the major product of this reaction will come from the tertiary carbocation, where now we have a Cl minus attacking the tertiary carbocation and forming our bonds. And if you want to track where the hydrogens are, that's where they are. Yes?
Can you explain the difference between the second structure from the left and the bottom? Is it just the position of the charge?
So from here, the first step, we're forming either a primary or a secondary carbocation. Now the primary carbocation is just out, right? We know it's less stable than the secondary. But once we form the secondary carbocation, because we have a potential forming a more stable tertiary carbocation, this will undergo a carbocation rearrangement, or if you think about the arrow pushing, is we're breaking the CH bond. And the electron of the CH bond, so we're breaking the CH bond here and forming the new CH bond here. All right, and then here we're left with a carbocation on the left carbon, which is the tertiary carbocation. So the actual reaction mechanism of the 1,2 rearrangement is a little bit more complicated than this lecture we want to cover. Just keep in mind that the 1,2 rearrangement or carbocation rearrangement is a highly kinetically fissile process. So whenever you end up drawing a secondary carbocation, look at your molecule and think about whether or not we have the possibility of forming a tertiary carbocation via a rearrangement reaction. Yes?
So in this case, we actually are moving atoms, not just electrons?
Correct. So these reactions were moving actual electrons. So these two structures are not resonance structures with each other. They are actual chemical reactions, but we're just saying the reaction is favoring the formation of the tertiary carbocation because it is more stable. But these two are not resonance structures with each other. Yes?
So does this only happen when you have secondary?
Well, secondary or primary, the overall goal here is carbocation rearrangement takes place to form the more stable carbocation. So it can be a primary to secondary, secondary to tertiary, right? So you're always forming the more stable carbocation in a carbocation rearrangement.
If it was primary, you can only do one.
What's that?
If it was primary, you can only do 1 and 2 and you stop there.
Well, if it's primary, you can do 1 and 2, but you can keep going, right? So you can keep going until you reach a point of the more stable carbocation. It can happen with hydrogen. It can also happen with an alkyl group. But if both alkyl and hydrogen are present, the hydrogen shift is favored over the alkyl shift. It's every time it's always one position. It's 1,2 shift. So it always shift to its neighboring position. All right, so as a summary, what do we know about hydrohalogenation? So it goes back to our original picture. So this is a general reaction, right? So what do we know? We know that first, the rate limiting transition state is our formation of the carbocation intermediate. So the first step is our rate limiting step. Secondly, the regio selectivity follows the Markov-Nikov rule. Or, in the other word, when we say Markov-Nikov, we're saying the hydrogen adds to the carbon with greater number of hydrogen. The real reason behind the Markov-Nikov rule is that we want to form the more stable carbocation intermediates. Here we make a link with what we discussed before, which is stability of carbocation, tertiary being more stable than secondary than primary. As a side note, we say that, okay, carbocations can also undergo 1,2 shift or carbocation rearrangement to form the more stable carbocation. And as an end note, the hydrohalogenation reaction is not stereospecific, because when my chloride anion or the X minus is approaching the carbocation, it doesn't matter which phase it's approaching to. Like if your carbocation is a planar molecule, the anion can come from top phase or bottom phase. It cannot distinguish which phase it is adding to. All right, so that's our hydrohalogenation reaction. That last question is about stereospecificity. Like for example, in this case, well, if this is a ethyl group, then obviously this is a new chiral center. But when that chloride is approaching, it doesn't know whether it's adding to the top phase or the bottom phase. So it's not stereoselective or stereospecific. How are we doing so far? This is your first organic reaction. Okay? And now let's take one more step. Now, in moving from hydrohalogenation, let's apply the same logic into a new reaction and see what can you predict from an unknown reaction following the same reaction mechanism. And that's why we care about reaction mechanism. So in this case, now we're looking at acid catalyzed hydration. Now in an acid catalyzed hydration, the typical reaction looks like this. So we have a double bonded carbon, hydrogen, hydrogen, hydrogen. Let's add a CH3 here just to make it fun. And the general reaction is this adds to a H2O molecule with acid. And in the products, we're following our Markov-Nikov rule of adding the hydrogen onto the carbon with more hydrogen. Oh, let me use a different color. And the OH on the other carbon. So it's Markov-Nikov selectivity. So what do we know about this reaction mechanism? If we ask you to write out the reaction mechanism, do we know how to do it? So let's do it together, right? So in this case, what do we have? We have a nucleophilic double bond. And in the reaction mixture, we have an electrophilic proton. All right, so what does my first step look like? In reality, my proton is my hydronium ion, or HOH. That's your H plus in water. So what does my first step looking at? The first step is my nucleophile attacking the acidic hydrogen to form the new CH bond. And then the oxygen, the OH bond is breaking, electron goes onto my oxygen. So this is my first step. And this first step is also my rate limiting transition state, or rate determining step. What's our product here? Now, You should know how to predict the site of addition based on the stability of the carbocation. Right, so if my hydrogen is adding onto this carbon, we're forming a primary carbocation. If the hydrogen adds onto this carbon, we're forming a secondary carbocation. So naturally, the favored product or the carbocation intermediate is the addition of your hydrogen onto the carbon with more hydrogen. It's a trigonoplanar, so let's make it more accurate. All right, so that's what we get. A secondary carbocation is more stable comparing to a primary carbocation. And hence, this is the origin of our regioselectivity. All right, some of the questions we might ask you is why not we're having a 1-2 shift. Like the question is why the 1-2 shift is not happening. So in this case, if we think about what does that 1-2 shift give us, we'll end up getting, well, a CH3, hydrogen, hydrogen, and carbon, which is on the primary position. Or the other way to put it is this 1-2 shift is forming the less stable carbocation, and obviously it doesn't happen. All right, so this doesn't happen. Now, what else? Now, from here, from this intermediate, what are we getting? We still have water molecules around. So in solution, you have H3O plus, yes, but at the same time, you also have neutral water. So if we have a neutral water around, now comparing this one and the carbocation intermediate, which one is the nucleophile and which one is my electrophile in the second pair? Yes.
Your carbocation is your electrophile.
Correct. And my water is my nucleophile. All right, so now in this case, my water, the lone pair on my oxygen now becomes nucleophilic. And the carbocation is now electrophilic. So when you're doing the arrow pushing for my second step, again, it goes from nucleophile to electrophile. So the arrow will naturally go like that. And what are we forming? Now we have carbon, hydrogen, CH3, oxygen, hydrogen, hydrogen plus, and carbon, hydrogen, hydrogen, hydrogen. Now again, in this process, thinking about the addition of your water onto your carbocation, again, this is not stereo-specific because we don't know which phase your water is going to attack your carbocation, so this is not stereo-specific. Yes?
Can you extend the water to nucleophilic? Isn't water neutral?
Well, water itself is neutral, but when we're looking at the relative nucleophilicity and electrophilicity between water and a carbocation, then your water is more likely to act as a nucleophile. There can be a potential side reaction of having an alkene acting as a nucleophile to add onto the carbocation. But what we're assuming here is in your solution, your water is way more abundant comparing to another molecule of alkene. So in this case, it's more likely your water is acting as a nucleophile to add onto the carbocation intermediate.
Yeah.
Next one.
That
So how do you know that H3O plus is present when you're forming the intermediate?
Well, this reaction is called acid catalyzed hydration. And we'll see H plus, so whenever H plus is around, you can assume you can start from H3O plus. It doesn't need to be very abundant, but you have to start somewhere, right? So this reaction doesn't take place without any acid. But as long as you add some kind of weak acid into the reaction mixture to get H3O plus in the reaction, it will catalyze the reaction. But we're getting there, right? So this is what we end. And we have one more step to form our final product, which is, well, we want to dissociate this OH plus, because now if we have another H2O around, comparing to these two molecules, now again, H2O is acting as a nucleophile. And this is your acidic hydrogen. So for our last step, we're having the nucleophile grabbing that acidic proton, breaking the OH bond to form our final product. And in this process, we are regenerating my HOHH, or the hydronium ion. So if you look at the overall reaction, we start from a H3O plus, we release a H3O plus for the reaction. So that's why this reaction is called acid catalyzed hydration. Right, we use a H3O plus, we end up regenerate that H3O plus. So looking at the reaction mechanism, we are regenerating the acid. That's why the acid itself is a catalyst. Yes?
Can you explain why the hydrogen on the water is the acidic one rather than the other molecules?
Which one?
Why is that hydrogen acidic rather than other ones?
This one?
Yeah.
Well, these two are the same. But if you're talking about the relative acidity of the hydrogen, now talking about going back to acid-base chemistry, when we're losing a hydrogen from this entire molecule, losing which hydrogen gives us the most stable conjugate base? That's the hydrogen attached to the oxygen, or in the oxygen ion. All right, so if we break this one, we're forming an alcohol, which is happy. But if we're breaking the CH bond, that's much less likely.
Yeah.
All right, so everything's connected. You see, like in today, when we're talking about reaction mechanism, we're using everything we discussed before, including acidity, arrow pushing, identifying nucleophile, electrophile, and predicting the stability of the carbocation intermediate. So we're using all the knowledge we discussed before in solving the reaction mechanism and using the reaction mechanism to predict the reaction outcome. Let's do a comprehensive example together for the acid catalyzed hydration. Yes.
Sorry, could you explain just one more time about how we have the extra waters, but we also start with some already hydrated water?
Now, so the way to think about it is what is inside my mixture. We have a chemical reaction mixture, and inside here, we have several different equilibriums going on. For example, your H2O and H plus is constantly undergo this equilibrium, right? So this tells me in my reaction mixture, both H3O plus and H2O are present. So in this case, when we're looking at the reaction taking place, we're always talking about relative nucleophilicity and relative electrophilicity. Now, in the first reaction, you have an alkene. This is not going to react with your neutral H2O because both of them are nucleophilic. What we want is a pair of nucleophile and an electrophile. So in this case, your alkene react with the electrophilic or acidic hydrogen or electrophilic oxynium ion. All right, so that's our first step. Upon formation of the carbocation intermediate, now we have a different situation. Now we have an electrophilic carbocation intermediate that want to react with some kind of nucleophile. All right, it can react with another alkene, but the reactant itself is at very low concentration. So thermodynamics speaking, it's more likely to react with a solvent molecule. Now, my solvent molecule here is now acting as a nucleophile. And then, upon formation of the oxenium cation, this then becomes, again, acidic. Right? It's, again, seeking for another nucleophile, and that's where the water comes from. So in organic chemistry reaction mechanism, when we're writing it, especially when we're doing all these arrow pushing, thinking about what is there, what is in my reaction mixture, what can potentially taking place. We're always looking at a pair of nucleophile and electrophile. Yes?
Does the equilibrium between H2 and H3 ever stop? Or like just stop as soon as you get to the end there?
Well, actually it doesn't stop here. Now acid here is not being consumed. The acid is being used and then regenerated. So if you're observing the pH of the reaction mechanism, it's actually not going to change too much because the acid is being constantly consumed. Now, whether or not we form this final alcohol or we end as the oxenium ion, that depends on the pH of the mixture. So in organic chemistry, it's very often people say, okay, upon the acid catalyzed hydration, we then add base to make it neutral, and then we get our final alcohol out, right? So these two will be in equilibrium with each other. These are just acid-base reaction. It depends on the pH of your reaction mixture. Yes?
So will you just stop once you regenerate the acid?
Well, that's just like one cycle of reaction, but as long as you have alkenes around, it will continue to react with water with an acid molecule present all the way until you finished up all the alkene. So I'm being like going very slow today. I hope this is a good demonstration to show you like how we're using everything we discussed before. Right, so thinking about what are the things we're using here. We're using the nature of the bonding in alkene. That's where we start from. We're identifying the relative nucleophilicity and electrophilicity of molecules. Right, we're practicing our arrow pushing starting from nucleophile to electrophile. We used our knowledge of the general mechanism where the rate limiting step is our slow step. We used the stability of carbocation to predict the regioselectivity of the reaction. All right? And then, in this case, we are also considering will a 1,2 shift or a carbocation rearrangement be fissile? And in this case, it's not. But in other scenarios, it might. We also discussed, like, because in this case, the addition is, it doesn't know, right? The overall environment is not chiral. So when your water is attacking the carbocation, it doesn't know which phase it is attacking. So the reaction is not stereospecific. All right, so we used everything we discussed before to come to the conclusion that the acid-catalyzed hydration is Markovnikov regioselectivity, non-stereospecific. So far, so good? And at the beginning of our next lecture, I'm running out of time, but it's okay. We'll do a comprehensive example of like, this is some kind of example you might see in your exam or your worksheet. That's we give you reactant and product, reaction condition. Ask you to write the IUPAC name, nomenclature. Ask you to predict the major product of the reaction. So that's what we discussed today. And propose a reaction mechanism and tell us what's the rate limiting step. So we'll pick up here. So if you like, try it yourself. All right, see you on Wednesday.